Before the appearance of GPS, relative theory was only known for several theoretical physicists. But after the GPS emerges, relative theory has become necessary in our daily life. For example, sailing of boats and travel through the desert. Also, there are a lot of concepts in relative theory we didn't know, but it has become a part of our life. With the progress of technology, we don't need maps or magnetic needle when we are lost. We can locate our location by using GPS. Global position system needs at least 3 satellites to complete positioning. Now, we assume that the ground time and the satellite time is the same. Then we use satellite and ground receiver passing the message of the time difference to calculate distance. And distance is equal to speed multiplied by time difference. And because the satellite message transmits by electromagnetic wave, and light is an electromagnetic wave too, so we can see the speed as the light, and the speed of light multiplied by the time difference, that is distance. But this is the theoretical value, so we can use the measurement called the space behind intersection to modify. It can do handling part from the arrow. Now we are going to have 3 satellites and the receiver on the ground to make 3 spheral equations. Then the equation for the intersection of the 2 spheres will be a ring. And the equation for the intersection of the third will be 2 intersections. One of the intersections is the receiver position. Another position may be in the Earth's interior or out space of the location. Originally, it's 3 satellite positions, but we can add the 4th satellite to make the location more precise.
Satellites will be affected by time dilation. In other words, the speed will affect the flow of time. Before proving time dilation, we talk about 2 laws first. One is the principle of relativity. In all inertial frames, the laws of physics have the same expression. Another is the principle of invariant light speed. In all inertial frames, the speed of light is constant. To prove time dilation, we can imagine an experience. There are 2 guys. One is on the ground, another is in a rocket with a velocity v. And they both have a light clock. As this picture, 2 mirrors with a particle of light bounding between them. We assume its distance is L. The time difference of 4 light bounding is delta t. So we can know this equation, delta t equal 2L divided by light speed. Another picture is the man on the ground. He sees the path of the particle of light, which is on the rocket. 2x is the distance that rocket fly through in delta t prime. Delta t prime is the time difference of 4 light bonding. D is the distance of half light bonding. So we can know another 2 equations. After our calculation, so we can know this time dilation equation. Delta t prime equal delta t divided by the square root of 1 minus b squared divided by c squared. And we know the speed of satellites is about 3,874 meters per second. So we can know the time in satellites will be slower than the ground, 7.2 seconds a day.
According to general relativity, the gravity will influence the time. And look at this picture. This picture shows that the gravity will bend the time-space plane. As the result, when light passes through this bent plane, it will cost much more time. So we can conclude that with more gravity, the speed of time will become more slowly. So as the result, satellite is much farther from the Earth, so its time is much faster than the Earth.
Now, we use the GPS receiver and the software Visual GPS to find the position of the satellite. Then, use a handmade electromagnetic telescope into a satellite. By using this way to locate the satellite where it is, because the electromagnetic telescope's length is a few times longer than the wavelength of the satellite. So it can make the standing wave to maximize the satellite signal. And the tube body with a metal foil can block off other satellite signal, so it called screening effect. Now, look at the picture. This is a azimuth photo. There are 5 steps. Number 1, place the azimuth on the right direction. We can use compass to find where north is. Number 2, use the software to select the satellite we want and figure out its azimuth and the elevation angle. Number 3, make electromagnetic telescope's nozzle aim to a satellite the direction we want. Number 4, use the protractor to adjust the elevation angle. Number 5, fine-tune the azimuth and the elevation angle to keep the strength of the satellite signal and reduce other signal. This is the end of experiment. Thank you.